Hello, good evening, students. Today we are going to solve one example using Booth's algorithm. So we are going to see how to solve any sign number multiplication using Booth's algorithm. And the example which we are going to solve was asked in TA1 examination and many students were not able to solve it. Okay, so today we will see how to solve such an example. Okay, so the example was -7 example was -7 into +3. So I'm expecting the answer as -21. Okay. So this on the right hand side, you will see one algorithm, which is Booth's algorithm. Okay. So while solving such example or any example using Booth's algorithm, your first requisite is that you have to draw the algorithm on the right side and then you have to solve the example on the left side. Okay. So first step in this is initialization. So to initialize, we are using the variables like accumulator, multiplicand, multiplier, and count represented as n. Okay, so accumulator is initialized to 0. So the number of bits for accumulator to represent a accumulator is equal to the number of bits used to represent m and q. So first we will represent m and q. So m is a multiplicand while q is a multiplier. Okay, so m is -7 and q is +3. Okay, so to represent +3 in binary, we all know 3 is represented as 0011 by using number of bits as 4. So 4 bits will be used to represent accumulator also and it will be initialized to 0. Similarly, q -1 is initialized to 0 as per this first step of initialization. Now, how to represent this m and n? So, number of count or count n will be equal to 4, which will be equal to the number of bits used to represent a, m, and q. Okay, so n will be equal to 4. Now, how to represent m? So, we know how to represent +7 in binary as 0, 1, 1, 1. But m is -7. So how to represent -7? -7 is represented in 2's complement form. So first we need to represent it in 1's complement by inverting each bit, then add 1 to it to get a number which will be 2's complement. So this will be equivalent to -7. Okay, so -7 is 1001 plus 7 is 0111. Okay, so this is very important. So you have to remember this. Now, this is your first step done. Now, to start with the second step, we need to start it by representing your A, Q, and Q minus 1. So, what is A? What is A? A is 0000. Q is your multiplier, which is 0011, and Q -1 is 0. So first we need to check these two bits Q0 and Q -1. So what is Q0 and Q -1? So I will use another color to represent it. So this is your Q0 bit and Q -1. How? This bit will be Q0, Q1, Q2, Q3. Okay, so we have to just check these two bits, that is Q0, Q -1, which is 1, 0. So if these two bits are 1, 0, which step I need to perform? A equal to A minus M. So my new value of A will be A minus M. Now, what is M? That is -7, right? So I will get it as A plus 7. In arithmetic or in any operation with the binary, we always prefer that arithmetic addition, which is very simple to perform as compared to subtraction. Okay, so it is easy to add -7 or 7 to A instead of subtracting -7 from E. Okay, so my value of A is now 0, 0, 0, 0. I'm going to add 7 to it. And what is my 7? 7 is 0, 1, 1, 1. So I will get new value of A as 0, 1, 1, 1. Okay, now, so this will be my new value of A. Q will remain as it is and Q minus 1 will be 0. Okay. Now, after this step, I need to perform arithmetic right shift of A, Q and Q minus 1 and my count will be reduced. So, initially my count is 4. Now, here in this step, I need to check. I need to perform arithmetic right shift and reduce my count by 1. Now, it will be 3. So, I will right shift this all bits. So, first MSB bit will be kept as it is and all other bits will be right shifted, that is A, Q and Q minus 1. Okay, so this is cycle number 1. Okay, so here count is reduced to 3 which is not equal to 0. So I need to again come to this step. Okay, so I will check again the value, the bits for Q, Q0 and Q minus 1. Now these two bits are 1, 1. As the both bits are 1, 1, as my Q0 and Q minus 1 is equal to 1, 1, what I need to do is I need to do arithmetic right shift and reduce my count. So I will just perform arithmetic right shift and now my count will be reduced to 0. So to perform arithmetic right shift, we will keep this bit as it is and all other bits will be consecutively shift towards right. Okay, so here again my second cycle is completed. Again I will check my count is not equal to 0. So again I will go to the first step. Okay, so again I will check the bits, that is bit number Q0 and Q minus 1. So now this combination is 0, 1. Okay, as it is 0, 1, as this combination is 0, 1, what I need to do is I need to perform E is equal to A plus M. Now here A plus, what is my M? M is -7. As I have said, we will always try to perform the addition operation in the binary. So what is now my A? A is 0, 0, 0, 1. And what is -7? -7 is this value, that is 1, 0, 0, 1. That is 2's complement of +7. So I will perform this addition. 1 plus 1 is 0. Carry 1. 1, 0, 1. So I will have a new value of A as 1, 0, 1, 0. Q will be as it is. Q minus 1 will be as it is. So this step is done. Now again arithmetic right shift and reduce the count. So I will perform arithmetic right shift and my count will be now reduced by one value and it will be equal to 1. So here to perform arithmetic right shift, this bit will be as it is and all other bits will be shifted towards right. 1, 1, 0 and this will be 0. Okay, so again this will be my third cycle completed. I will check the count. It is 1. It is not equal to 0. So I will again go to this step and I will check the bit, that is Q0 and Q minus 1. Okay. So I will check these two bits again. Now these two bits are 0, 0 as these two bits are 0, 0, again, I will directly perform arithmetic right shift and count will be reduced by 1. Now the count will be 0. So to perform arithmetic right shift, this bit will be as it is 1, 1, 0, 1, 0, 1, and this will be 0. Okay, now this will be your fourth cycle. Now count, I will check, it is 0. So I will end this algorithm. And after this step, I am expecting my product should be holded by these two registers, that is A and Q. So A and Q combinedly will hold the value of will hold the my product term, which will be of 8 bits. Okay, and this product I'm expecting as a minus 21. Of course, it is not plus 21, right? So this will be always in the sign value, as my one of the element while performing multiplication is a sign component, sign element. So the product will be sign. And whatever answer I will get, that answer will be in a 2's complement form. So if I want to check whether my answer is really equivalent to 21, then I will just take 2's complement of this product. That is, to take 2's complement, first I will take 1's complement. Okay, so first I will take 1's complement. So to take 1's complement, just invert all this bit. Okay, so this is 1's complement, add 1 to it. You will get 1, 0, 0, 1, 0, 1, and this is equivalent to plus 21. That means the product which I got, this is correct one. Okay, so in this way you can solve any example. Only the steps you need to remember is, first is you need to draw your algorithm on the right hand side, and step by step you need to solve this example on the left hand side. This step is important while performing the subtraction, what your value of m is, whether it is positive or negative. And accordingly, you will get this term, because this is the main and important term which is actually holding your final product value. Okay, so the accumulator value is very important. So any mistake done in accumulator and the Q value, then you will not get the correct answer. Okay, so the multiplicand, your multiplier, and accumulator, these three are important to start and to end with the correct answer. Okay, so all the best for your examination. I hope you all have got it. If there is any query, you can just reach out to me. Thank you.